And welcome to another screencast. This is Nick Andre, and in this screencast we will explore the Transmission Control Protocol, also known as TCP. The transport layer provides transparent transfer of data between end users by providing reliable data transfer services to the upper layers. The transport layer controls the reliability of a given link through flow control, segmentation/desegmentation, and error control. This means that the transport layer can keep track of the segments and retransmit those that fail. To initiate a session, the Transmission Control Protocol uses the three-way handshake technique. The three-way handshake is used by TCP to determine if the destination device exists, verify that the destination device has active services running, and are able to accept the incoming request. This handshake also helps to inform each host which ports are being used for communicating. The client begins the three-way handshake by creating an initial sequence number and setting the sync flag on. In this particular example, the sequence number is set to 0, and the sync flag is the only flag that's active. You can tell that I am trying to open up a telnet session because my destination port is 23. Because the client is initializing this conversation, it is set a dynamic port of 49,152. Which is my source port for every segment from here on out. You will also notice that the acknowledgement number is left empty. This is because the clients initiate the conversation, and because this is the first step of the conversation, I have nothing to acknowledge. Let's pass this segment to the server. The server acknowledges the client's request by setting its acknowledgement number field equal to the client's initial sequence number plus 1. In this particular case, my acknowledgement field now has the number 1 because my initial sequence number was 0. 0 plus 1 allows me to store 1 in the acknowledgement number. In addition to the acknowledging the client's request, the server needs to start a download stream to the client. Hence, it creates a unique sequence number of its own and stores it in the sequence field. The sequence field in this particular segment has initial value of 100. And that value is colored red for us to indicate that this is the server's sequence numbers and not the laptop's. You will also notice in this segment that both the source and the destination have switched their location. Now this is coming from the server, so I use port 23, and it's going back to the laptop, so I'm putting the 49,152 to address the telnet software running on the laptop. Let's send this segment to the laptop to let them know that I am trying to open up a download session and I am accepting their upload stream. The client will respond to the server's request by sending a segment back with the ACK flag turned on and the acknowledgement number field set to the server's initial sequence number plus 1. Much in the way that the server acknowledged the laptop is acknowledging the server's download stream request. As you can see, this number is in red to sort of synchronize the two together. Control bits or flags are used to indicate the status or progress of a session. A sync flag is used to request a connection to the receiving host. The ACK flag or acknowledgement is used to inform the sender that they received the last piece of data and to send the next piece being the number stored in the acknowledgement number field of the header. To complete this three-way handshake, the segment needs to be passed to the server, so the server is aware that the laptop has given it permission to start its download stream. Now that the session is created, TCP has the mechanisms in place to keep track of segments that are coming and going, whether it be from the laptop or from the server. Wireshark is a network protocol analyzer used by many network administrators. It lets users capture and interactively browse the traffic running on a computer network. It is the de facto standard across many industries, including educational institutions. Every once in a while, you will see Cisco reference a typical screenshot of Wireshark. In this particular screenshot, we can see how Wireshark is used to capture the first stage of the three-way handshake, session establishment. I know this to be true because this particular header lacks an acknowledgement number field and the sync flag is set. Instead of acknowledging every byte the laptop receives, the server sets the window size to 10 bytes, informing the laptop to send an acknowledgement after every 10 bytes. Notice, in the second segment sent by the server, the sequence number is 106, 5 bytes more than the last segment. That is to say, byte 0, the first byte, would be sequence 101, byte 1, the second byte, would be sequence 102, byte 2, the third byte, would be sequence 103, byte 3, the fourth byte, would be sequence 104, and byte 4, the fifth byte, would be sequence 105. The next byte, byte 5, would be sequence 106, representing the next segment. How large a segment is can vary on the transmission capacity of the medium. Also notice that both the acknowledgement and the ACK flags are the same for each segment. Remember, segments can arrive out of order. Hence, segment 105 could arrive before segment 101. Therefore, both segments contain the same acknowledgement data to inform the receiving host what came in last and what they are expecting next. This is called expectational acknowledgement. In this case, the server receives segment 1 and is expecting segment 2 the next time the laptop sends something back. Because the window size was set, the laptop must send an acknowledgement back to the server once it receives 10 bytes. Before the server can send any more data to the laptop, one or two things must happen. Either the server receives an acknowledgement from the laptop telling it what segment to send next, or its wait timer has expired. If the server's wait timer expires, it will retransmit the last 10 bytes that were not acknowledged by the laptop. Waiting for the acknowledgements could generate a lot of overhead and additional delay when transferring files. Setting the window size of a session helps to minimize these delays. In this case, our server does receive an acknowledgement from the laptop. As a result, the server ships the next two segments, segment 111 and segment 116. So to acknowledge what the laptop has sent, both segments' acknowledgement flags are set and the acknowledgement number field to 3, the next segment it expects to receive from the laptop. As expected, the laptop, after receiving 10 bytes from the server, sends acknowledgement back to the server. This process continues until the server is finished delivering the file. To terminate a session, each one-way TCP connection must be closed. To close a connection, it requires 2 steps per each stream. If the client has nothing more to say, it will send a segment with a FIN flag set to the server. The server acknowledges the client's request by sending an acknowledgement back. This would close the upload stream. When the server is finished, it will set and send a FIN back to the client to terminate the download stream. To close this session, the client will respond back with the ACK flag set. Let's see these steps in action. Step 1. The host must send a segment with the FIN flag set. Since this segment will be set after receiving incoming segment, the host, in this case the laptop, will also set the ACK flag, letting the server know what segment it received. The sequence number of the next incoming segment will be stored in this segment's acknowledgement field as well. The second step of this process requires the other host, in this case the server, to acknowledge the sender's request to close the connection. To do so, a new segment is set back with the ACK flag turned on to acknowledge the laptop's request. Of course, the server will set the acknowledgement field to the next incoming segment it expects to receive. Notice these 2 steps are used to inform the server that the laptop is closing its upload connection. That is to say, the next time the laptop would like to transmit data to the server, it will have to set and send the SYN flag to a new segment. The laptop, however, will continue to acknowledge incoming segments even though its upload stream is closed. The upload stream is only used when the client has data to send back to the server's process. When the other host, in this case the server, is finished, it will set and send the fin flag to the receiving host, thus completing the third stage of the four-way handshake. The receiving host will respond by setting and sending the ACK flag back to the server, hence to close the session. In order to close the session, it will require 4 steps to terminate, 2 per each one-way connections. Networking administrators can view active connections using the netstat command. In this example, the local host has 3 active sessions: a secure web connection, an incoming email connection, and a common web connection. The time wait state is activated when a fin is set, and now the client is waiting for an acknowledgement. Until both sides close their connections, the client will still consider this as an active connection. To prevent the host from being overwhelmed by incoming segments, TCP implements a technique known as dynamic window size. Dynamic window size controls the flow, or the rate in which segments are sent and acknowledged. This helps to prevent the loss of segments caused by limited resources, thereby avoiding the need for retransmission. This technique also helps to detect and fix errors caused by dropped segments. If both hosts support selective acknowledgments, it is possible for the destination to acknowledge bytes in non-continuous segments, and the host would only need to retransmit the missing data. In this example, the window size is set to 3000, which means the receiver will send an acknowledgment after every 3000 bytes. Unfortunately, bytes 3001 to 4500 were lost on their way to the receiver. Unaware of this, the sender keeps sending until it sends all 3000 bytes. Once it reaches the window size, it waits until the receiver notifies the sender what it is missing. In this case, the receiver is missing segments 3001, hence an acknowledgement of 3001 is sent back with a window size of 1500. Now the sender will retransmit the missing bytes. The next acknowledgement the receiver will send will be 6001, not 4501, because bytes 4501 to 6000 were successful. The receiver will probably keep the window size to 1500 until a few successful segments have arrived. Changing a window size on the fly is known as dynamic window sizing, and as stated earlier, is used to prevent loss of segments. What if both segments were not received? How would the sender know when to retransmit those missing segments? In this case, the sender realizes that segment 1200 wasn't received because the receiver either did not receive segment 1200, hence no acknowledgement was sent back, or it did receive segment 1200, but the sender gave up waiting for the acknowledgement. In either case, the timer expired and the sender retransmitted segment 1200 to the receiver. In this screencast, we discovered that TCP does not pass data to the network until it knows the destination is ready to receive it. TCP then manages the flow of the data and resends any data segments that are not acknowledged as being received at the destination. TCP uses mechanisms of the three-way handshake, timers, acknowledgments, and dynamic windowing to achieve these reliable features. This reliability does, however, impose overhead on the network in terms of much larger segment headers and more network traffic between the source and destination managing the data transport.